Hi, this clip is designed to take on a little bit of extension work now. It's related to the box on page 228 of your textbook, and it looks at what happens if you have the same halogen atom but on three different haloalkanes, but each haloalkane has a different structure in terms of whether it's primary, secondary or tertiary. So let's just remind ourselves of the three types of haloalkane structure. So we have primary, secondary and tertiary. Now the thing about primary, secondary and tertiary structures, whether it's haloalkanes or any other type of structure, is the number of R groups that are attached to the carbon to which the functional group is bonded will influence how stable the carbocation that's formed could be. So to think about this, we need to remind ourselves of Markovnikov's rule, which we looked at when we did alkenes. So in other words, the more R groups there are, alkyl chains, that is, on the carbon atom to which the halogen is attached, the greater the stability of a carbocation that could be produced if we were to remove that halogen. So let me show you what I mean. So if you have three carbocations going from left to right, primary, secondary and tertiary, they increase in stability in this direction, meaning this is most stable and this one here is least stable. So this has an effect on the mechanism that takes place when they're hydrolyzed, and therefore that has an effect on the speed with which they're hydrolyzed. So don't worry, one is not a new mechanism, they're both considered nucleophilic substitution. So what I'm going to do is split the page down the middle like this, and we're going to take a primary haloalkane with its one R group, and then we're going to take a tertiary haloalkane with three R groups. But notice that the halogen is the same type. So we're not comparing the carbon-chlorine bond to the carbon-bromine bond, for example, like we were doing before. So don't forget we've had to put in our dipoles because we're going to draw the mechanism. So on the left hand side, what happens is just like before, we have our incoming OH minus. It moves to the other side of the carbon for the reasons that were explained in the video. Basically, the other side of the carbon is less likely to be repelled by the slightly negatively charged chlorine, and therefore you get a heterolytic splitting of the carbon-chlorine bond, and the electron pair that was a bond pair moves on to the chlorine atom, and that gives us down here a new bond between the carbon and the OH, like that. So this process occurs in one step. The other one with the tertiary haloalkane on the right hand side, that occurs with two steps. So I'm just going to label the two haloalkanes to remind you of which one is which, and I also need to add the outgoing chloride ion as well. So on the right hand side, coming back to it, we have an OH group that again moves towards the positive carbon, but before it actually bonds with it, look what happens. If we just briefly get rid of that for a second, we concentrate on the carbon-chlorine bond. The OH is still out there in the vicinity, like so. But the carbon-chlorine bond breaks first. That gives us a tertiary carbocation, which is stable, like we've just said. And what the OH can do, if we draw it again down here, is attack that. And that gives us, finally, our product. Let's make a bit more room there. Okay. And we also have, obviously, the Cl-. So you'll have two steps here. So the first step is for the carbon-chlorine bond to break heterolytically. So that takes place at the top of the page, top right-hand corner. And the next thing to happen is that at the bottom, where the OH attacks the carbocation, that's your second step. So it's a two-step process. So now let's have a think about what's happening when you have a primary haloalkane versus a tertiary haloalkane with the same alkane attached, which is faster. So in red you've got a justification as to why the primary haloalkane is hydrolyzed slowly and the tertiary haloalkane is hydrolyzed quickly.